Section. Introduction. We're going to talk about large language models, LLMs, which have proven to be quite versatile. They can reason, generate coherent language, and even have a grasp of world knowledge. People have been fine-tuning these models to perform specific tasks like generating code, editing text, and solving math problems. This has led to the creation of many specialized models, each with its own unique capabilities. For instance, some models are great at generating code but struggle with logical reasoning, and vice versa. This brings us to an interesting question. Can we combine a general model with a specialized one to create a model with new abilities? For example, could we merge a model that understands code with a language-generating model to create a model that can translate code into text? The usual way to do this is to further train the general model using the data that was used to train the specialized model. However, this isn't always possible. Training large models can be costly in terms of computation, especially if the specialized model is also a large language model trained on a huge amount of data. There might also be issues with data privacy or organizational boundaries that prevent us from using data from multiple sources. Working with multiple distinct models is also desirable because it allows us to reuse existing models with established capabilities, providing better control and avoiding the problem of catastrophic forgetting that is common in conventional approaches. To tackle these challenges, we propose a practical setting for model composition. We have access to one or more specialized models and a general model. We can't modify the weights of either model, and we only have a small amount of data that represents the combined skills of the models, like code generation with complex logical reasoning. Previous attempts to combine models have either tried to route between the models or merge them, but neither approach is effective in this setting. Routing between models, or choosing the output of one model over the other, doesn't work when neither model has the desired capability. Merging models by combining their parameters also has limitations, especially when the models are of different sizes and have different training objectives. In this work, we propose a new framework called Composition to Augment Language Models, Comm, to address this model composition setting. Comm introduces a small number of trainable parameters over both the specialized and general models' intermediate layer representations. It finds an effective combination of the models to perform new challenging tasks more accurately than either of the models alone, while preserving the capabilities of individual models. We study two practical applications of Comm: language inclusivity and code generation. For language inclusivity, we use a model that has been trained on a set of low-resource languages. We find that combining this model with the LLM allows us to significantly improve performance on translation and arithmetic reasoning tasks for low-resource languages. For code generation, we use a model that has been trained on open-source code across a variety of programming languages. Combining this model with the LLM, borrowing its low-level logic and generation capabilities, outperforms the two base models on code explanation and code completion tasks. There are other works that focus on efficient ways of fine-tuning models for new domains by introducing a small number of trainable parameters, keeping the original model intact. However, it's challenging to use this approach to adapt a model to a new domain, which is absent from the original training corpus. In contrast, Comm enables a model to be adapted to completely new domains using a specialized model. We demonstrate that Comm is significantly more effective than LoRA, a representative parameter-efficient fine-tuning method. There are also methods that merge different expert models with simple techniques like task vector averaging. However, these methods are only relevant when the original models are well aligned. Other related approaches are also applicable only when the models are derived from the same model or they are of the same size. In contrast, Comm is more generic and is applicable to any set of models. Section Summary. Large language models, LLMs, have been fine-tuned for specific domains, but combining them with augmenting models to enable new capabilities is challenging due to computational costs and data privacy concerns. To address this, we propose the Composition to Augment Language Models, Comm, framework, which introduces trainable parameters over both the augmenting and anchor models' intermediate layer representations. Comm effectively combines the models to perform new tasks more accurately while preserving their individual capabilities. Comm outperforms base models and other fine-tuning methods in language inclusivity and code generation tasks. Section. Model and task compositionality. We're going to discuss a method that involves the use of multiple language models to solve a task. This method is based on the idea of reusing and combining different models, each with their own unique capabilities. This concept has been explored in previous studies from a multimodal perspective, where cross-attention parameters were introduced across a language model to focus on representations from an image encoder. This resulted in a successful transfer of capabilities between the two models. In our work, we're extending this concept to include the composition of capabilities in a large language model. We're also looking at how multiple language models can be used as tools to solve a task. This involves composing in the model's input text space. There's potential to investigate if other models can be incorporated into the same framework. However, these approaches require a lot of prompt engineering, so we're focusing on composition through representations that can be learned automatically. We're introducing a method called composition to augment language models, Comm. This involves combining an anchor model, let's call it Model B, and an augmenting model, Model A. The aim is to create a new model that has new capabilities as a result of combining the capabilities of the two individual models. We're doing this under certain conditions. We can access the weights and intermediate representations of both models, but we can't change the weights or access the training data, hyperparameters, or training states of both models. We're also given a few examples from the target composition domain. The goal is to learn a composition to achieve a joint task. The weights of models A and B are kept constant, and we introduce additional trainable parameters to learn the composition. We're always operating over a selected set of layers from models A and B. We learn two sets of additional parameters over these layers, a simple set of linear transformations that maps a layer representation from model A to the dimensionality of representations from model B, and a set of cross-attention layers that cross-attend between this transformed layer representation and a layer representation from model B. Let's say models A and B have NA and NB layers respectively, and DA and DB are the token dimensionality of the two models. We first choose a set of compositional layers for both models, over which the new learnable parameters are introduced during composition. We then map representations from model A to that of model B via a projection layer. This enables cross-attention across models and aligns representations from models A and B despite the weights of the base models being frozen. We also introduce cross-attention between representations of the anchor and the augmenting model. We use the projection from the augmenting model as the key and value vectors for each head in cross-attention, and the vector from the anchor model as the query vector. The cross-attention output is added as a residual connection to the layer representations of model B. The resultant output vector is the input to the succeeding layer in model B. All layers are utilized in a similar manner. Propagating over the remaining layers in model B gives us a final output token decoded for each time step. The output token for each time step is appended to the input, and the updated input at each time step is passed to both models, refreshing all representations for the two models. Section Summary. The paper introduces a method called composition to augment language models, Comm, that aims to combine the capabilities of two individual language models to enable new functionalities. The composition is achieved by learning a set of additional parameters that allow cross-attention between the two models, resulting in improved representations and joint task performance. The method focuses on automatic learning of composition through representations, without requiring access to training data or the ability to change the weights of the base models. Section. Since the target model $M, $text A, O plus text B, involves a composition over the two models $M, $text A, and $M, $text B, we construct the set of training examples $D, C, text, to depict a combined skill that enables $theta C, to attend over the two models appropriately for the target task. Ideally, if the set of tasks involved in composition task are distinguished as $T_1, $and $T_2, respectively, then we design $D_C, text, to depict the adjoint task $C. For example, with respect to our synthetic key value setup, our final task, $C, is to perform arithmetic over a set of keys. The augmenting model $M, $text A, is trained to learn the given key value pairs, notated as task $T_1, and the anchor model $M, $text B, $is generic model that can perform numeric arithmetic well, task $T_2. For learning the set of parameters $theta_C, for composition, we consider $D_C. Text. To arithmetic over a held-in set of keys, task $C, encompassing combined skills from the two models. In contrast to fine-tuning approaches like LoRA that would require the entire knowledge source, here, key values, during training time, we find that training composition on only a fraction of the keyscan generalizado the full set. In other real-world settings, a clear distinction in specializing tasks for each model might be difficult to formulate, and hence defining a task that captures the combined skills can be challenging. We find that using a set of examples that capture certain capabilities of the two models suffices, i.e., some rough notion of $T_A_B. For our language inclusivity task, we use a mixture of examples containing a small amount of low-resource language and high-resource language data. We're going to talk about how we create training data for a model that combines two other models. Let's call the combined model M, and the two models it's made up of A and B. We want M to be able to use both A and B effectively for a specific task. To do this, we create a set of training examples that represent a combined skill from both A and B. If we think of the tasks that A and B are good at as T1 and T2, we design our training examples to represent a joint task, which we'll call C. For instance, in our synthetic key value setup, our final task, C, is to perform arithmetic over a set of keys. Model A is trained to learn the given key value pairs, task T1, and Model B is a generic model that can perform numeric arithmetic well, task T2 inches. To learn the parameters for the combined model, we consider our training examples to be arithmetic over a set of keys, task C, which requires skills from both A and B. Unlike other methods that require the entire knowledge source during training, we find that training the combined model on only a fraction of the keys can generalize to the full set. In real-world settings, it might be hard to clearly define tasks for each model, so defining a task that captures the combined skills can be challenging. We find that using a set of examples that capture certain capabilities of the two models is enough. We also want to note that while we've talked about combining one model A with one model B, our method can be applied to multiple models. This would require learning similar projection and cross-attention components between the anchor and each of the augmenting models. We'll leave a thorough investigation of this for future work. We've tested our method in 3 domains. 1. We've shown that an anchor model can be combined with an augmenting model trained on mappings between string keys and number values to solve arithmetic expressions over those keys. This requires both knowledge of the key value mappings and arithmetic capabilities. 2. We've shown how our method can be used to expand the language coverage of an anchor model to low-resource languages it hasn't seen during pre-training. An augmenting model pre-trained on low-resource languages can be combined with such an anchor model to significantly improve translation and math word problem-solving capabilities in low-resource languages. 3. We've shown how code completion and explanation can be improved by combining an anchor model with an augmenting model specializing in the code domain. In all experiments, we started with a basic model and further trained it on domain-specific data to create an augmenting model. This augmenting model was then kept frozen during the combination process. We didn't use any task-specific training data to train our method. We used larger models as the anchor model, which was also kept frozen during the combination training. For all our experiments, we performed the combination using every fourth layer output from the augmenting model. Correspondingly, layers from the augmenting model were chosen such that the number of layers in both models was equal. Finally, we studied a setting where we have a small model that has been trained to memorize string to integer key value mappings, and a large model that is capable of performing arithmetic over integers. We used our method to combine them and enable a new capability of solving arithmetic expressions containing those keys. Section Summary. The composition training data is constructed to enable the target model to appropriately attend over the two models involved in the composition task. The training examples depict a joint task that combines the skills of the two models, such as performing arithmetic over a set of keys. The method can be applied to multiple augmenting models as well, but further investigation is needed. Section. Key Value Domain Knowledge. We start by creating a database of key-value pairs, with 25,000 pairs in total. We generate these pairs by selecting English strings of 2 to 6 characters from the vocabulary of a model called POM2XXS and assigning them unique integer values ranging from 1 to 25,000. This database is our knowledge artifact. Next, we create a set of arithmetic expressions involving addition, subtraction, and multiplication operations between 3 to 6 keys. These keys are randomly selected from our knowledge artifact, and the operations to perform between them are also chosen randomly. Using these arithmetic expressions, we generate 3 different datasets. 1. The first dataset, called KV substitution, maps each arithmetic expression to an expression where the keys are replaced by their corresponding values. For instance, an example in this dataset might look like less than K1 greater than plus less than K2 greater than less than K3 greater than 10 plus 22 to 24. 2. The second dataset, called KV arithmetic, maps each arithmetic expression to the numeric value obtained by solving the arithmetic expression when the keys are replaced by their corresponding values. An example in this dataset might look like less than K1 greater than plus less than K2 greater than less than K3 greater than 8. 3. The third dataset, called numeric arithmetic, maps the value substituted version of each arithmetic expression to the numeric value obtained by solving the arithmetic expression. An example in this dataset might look like 10 plus 22 to 24, 8. We then train a model, called the augmenting model, on the KV substitution dataset to make it memorize the key value pairs in our knowledge artifact. However, this training does not teach the model how to solve arithmetic expressions. We also use a pre-trained model, called the anchor model, which is capable of solving numeric expressions with decent performance. This model, however, does not know about the key value pairs in our knowledge artifact. We then take examples from the KV substitution dataset that only cover 20% of the keys in our knowledge artifact to form the training data for composition. We use this data to combine the augmenting model, which knows about the key value pairs, and the pre-trained anchor model, by training the composition parameters using a method called Comm. Both the augmenting and anchor models are kept unchanged during this process. We evaluate the combined model for its ability to solve arithmetic expressions containing keys from our knowledge artifact. We do this by testing it on a subset of the KV arithmetic dataset that does not contain expressions used during training. This allows us to measure the model's ability to generalize to keys beyond what was observed during training. The results show that the augmenting model performs well on the KV substitution task, achieving 98.1% accuracy, indicating that it has memorized the key value pairs well. However, it performs poorly on the numeric arithmetic task, with only 4.2% accuracy, showing that it lacks arithmetic capabilities. As expected, the anchor model gets 0% accuracy on the KV substitution and KV arithmetic tasks as it has not seen any data from our knowledge artifact. However, it performs well on the numeric arithmetic task, with 73.7% accuracy, demonstrating its ability to perform arithmetic operations over numerals. Finally, the combined model is able to solve all tasks with high accuracy, especially the KV arithmetic task, with 84.3% accuracy, which both the underlying models fail at. This shows that the combined model is able to leverage the relevant capabilities from both the augmenting and anchor model to solve a complex task. Section Summary. The authors first generate a repository of key value pairs by sampling English strings and assigning them unique integer values. They then generate arithmetic expressions using these keys and operations, and create 3 datasets, one with the keys replaced by their corresponding values, one with the numeric value of the expressions, and one with the value substituted expressions. They train an augmenting model on the value substituted dataset and an anchor model on the numeric expressions. They evaluate a composed model, which combines the capabilities of both models, and find that it performs well on all tasks, especially the arithmetic task that the individual models struggle with. Section. Low Resource Language Inclusivity. In this section, we're exploring whether we can combine a large anchor language model, which we'll call Model B, with a smaller augmenting language model, Model A, that's been trained on languages that aren't widely spoken. We want to see if this combination can handle translation and math problem-solving tasks in these less common languages. We're using a set of languages and associated data from the Next 1000 Languages, NTL, project as our source material. This large-scale dataset includes sentences and translation pairs for around 1,000 languages, gathered from the web. It's been used before to expand language models and translation systems. To create Model A, we trained a small model called POM2XXS on the NTL data, to give it knowledge of these less common languages. For Model B, we used a pre-trained model called POM2S. We used about 5% of the NTL data as training material to combine models A and B using a method called Comm. Neither model is trained during this combination process, and Model B doesn't receive any training on the less common language data. We tested the combined model, which we'll call Model A plus B, on 2 tasks. The first was translating text from a non-English language to English, using a dataset called Flores 200, which includes examples from 200 languages. The second task was solving grade school math problems written in a non-English language, using a multilingual version of the GSM-8K dataset, which includes math problems in English and 9 other widely spoken languages. We also created a version of the GSM-8K dataset for less common languages by automatically translating the English problems into 25 less common languages. Our results showed that Model A plus B outperformed both Models A and B on the Flores 200 dataset for 10 less common languages. In fact, Model A plus B outperformed Model B on 175 out of 192 languages. On the GSM-8K math problem task, Model A didn't perform well due to its limited math reasoning abilities. However, Model B did much better thanks to its math reasoning abilities and its training on widely spoken languages. Model A plus B outperformed both Models A and B on 18 out of 25 less common languages and 9 out of 10 widely spoken languages. We also found that fine-tuning Model B on the NTL data actually made its performance worse, indicating that it was forgetting some of its training. However, combining Model A with Model B using Comm avoided this problem. Finally, we looked at code understanding and generation, which require 2 different types of knowledge: understanding the syntax and semantics of code, and understanding the real-world context that the code is dealing with. Large language models have a lot of real-world knowledge, but they might not understand code syntax if they haven't been trained on enough code data. On the other hand, small models trained specifically on code data might understand code syntax well, but lack real-world knowledge and reasoning abilities. Using Comm to combine these 2 types of models could give us the best of both worlds. Section Summary. In this section, the authors investigate the possibility of combining a large language model, LM, trained on high-resource languages with a smaller LM trained on low-resource languages to perform translation and math word problem-solving tasks in these low-resource languages. They use a dataset containing web-crawled sentences and translation pairs for 1,000 languages, and evaluate the composed model on translation tasks and math word problems. The results show that the composed model outperforms both the individual models, demonstrating the effectiveness of model composition. Additionally, the authors discuss how Comm, composed adversarial language model, can enable the combination of code understanding and generation capabilities in language models. Section: Code Domain Data. In this section, we discuss our approach to code domain data. We use a specific collection of open source code, which we'll call Code Dataset, taken from various programming languages on GitHub. We use this data to train our first model, which we'll refer to as Model A. We use a version of the POM2XXS model, which has been further trained on the code dataset, as Model A. Meanwhile, the base pre-trained POM2S model serves as our second model, Model B. We create a combined model, Model A plus B, by training it with only 7% of the same code data used for Model A, to ensure data parity. We test the effectiveness of our combined model on 3 tasks. 1. Code completion, CC. The model is given a few lines of code and is asked to complete the code snippet. This task tests the model's understanding of code syntax. We use the Human Eval benchmark dataset for this task and report the pass at 1, p at 1, metric. 2. Text to code, T2C. The model is given a text and is asked to generate the corresponding code snippet. This task tests the model's language understanding and code generation capabilities. We use the MBPP dataset for this task and report the p at 1 metric. 3. Code to text, C2T. The model is given a code snippet and is asked to generate a natural language explanation of the code. This task tests the model's code understanding and text generation capabilities. We use the code XGLUE benchmark for this task and report CHRF1 scores across languages. Our results show that Model A, which was trained on the code dataset, has a better understanding of code syntax. On the other hand, Model B, due to its larger scale and general-purpose pre-training, performs better on the T2C and C2T tasks. When we combine the two models using our method, we see a clear improvement in performance, 6.1% and 3.6% absolute gains over Model B on the CC and T2C tasks, respectively. However, we noticed that fine-tuning Model B on the code dataset led to a significant drop in the C2T performance due to catastrophic forgetting. Our combined model retains the performance and is slightly better than Model B across all languages. We also studied the influence of Model A by replacing it with simpler and random versions during composition. We found that there was a significant drop in performance across all tasks with these simpler versions. This suggests that the performance gains seen with our method are a result of using Model A and not the added parameters. Finally, we also explored a variation where we use Model A as an encoder, meaning an output token decoded at a given time step is not added to Model A's input. In this case, only the prefix representations of Model A are used. This approach led to a significant decline in performance across our tasks. Section Summary. In this section, the authors describe the use of a code-specific corpus to train their Comm model, which combines two pre-trained models, one specialized in code syntax and the other in general language understanding. They evaluate Comm on three tasks: code completion, text-to-code generation, and code-to-text generation, and report improved performance compared to the individual models. They also analyze the influence of the specialized code model and the use of iterative decoding, finding that both factors contribute to the improved performance of Comm. Section: Comparison with LoRA. We'll now compare our method with LoRA, a parameter-efficient fine-tuning approach. In this comparison, we train LoRA layers to adapt a certain model, which we'll refer to as MB. For all our experiments, we adjust the LoRA rank so that the number of parameters added matches the number of parameters introduced with our method, Comm. We also train LoRA using the same data as Comm, which we'll call DC. When we look at the results, we notice a significant difference in performance between the two methods across all tasks and metrics.